What happens if you fall into a black hole? Do you get turned into atomic spaghetti? Or is it a doorway to another world?
The math allows for exotica. The observations are much stricter. Today we'll separate what's solid science from what's just a pretty hypothesis.
Hi, this is the podcast Does Time Exist? I'm Emma Harper. We talk about the cosmos honestly and without mystique, verified facts, clear explanations, and a healthy dose of skepticism.
I'm Dr. Nathan Cole, a physicist. Today we're going after the biggest, strangest questions. Is the universe infinite? What is inflation? Was there a before the Big Bang? And most importantly, could a black hole be a portal?
Our deal is simple. Where there are measurements, we say we know. Where it's theory, we say maybe. No sensationalism, curiosity only.
We'll run from redshift and the Hubble law to the information paradox and Penrose's ideas about time. We'll define terms as we go: event horizon, spaghettification, quantum vacuum, in plain language.
Ready? Helmet on. Part 1, is the universe infinite?
People keep asking whether the universe has an edge. If it does, where is it? And if it doesn't, why are we so confident about that? Where's the right place to start this conversation?
Start with the practical idea of the observable universe. That's not all of reality. It's the enormous bubble of space around us from which light and any other signals have physically had time to reach our instruments over the finite lifetime of the cosmos. The boundary of that bubble isn't a cosmic wall, it's an information limit. Because the speed of information is finite, some far-off regions simply haven't had time to tell us they exist. By the numbers, the radius of the observable region today is about 46 billion light-years in every direction, which is larger than the age of the universe in light-years for a very down-to-earth reason. While photons were traveling toward us, space itself was stretching, so their path ended up longer than naive arithmetic suggests. The better metaphor isn't a fortress wall, it's an ocean horizon. The sea doesn't end at the line of sight. Beyond it, we just lack information.
If that boundary is an information limit, not a physical barricade, how do we figure out the shape of the stage everything plays out on? What does geometry tell us?
When we combine measurements of the cosmic microwave background, the statistics of galaxy clustering, and other independent cosmological tests, we keep landing on the same picture. On very large scales, space looks close to flat. That means if you built gigantic triangles out of light rays, their angles would sum to almost the Euclidean value, and volumes and areas follow nearly the same formulas you learned in school. But curvature isn't the whole story. There's topology, the global stitching of space. You can have geometry that's locally flat yet globally quirky, so that moving in a straight line eventually brings you back to where you started. In 3 dimensions, that could look like a volume with opposite faces glued, letting light lap the universe and paint repeating patterns on the sky. People have searched for such repeats in the microwave background for years and haven't found convincing ones. The cautious takeaway: our observable patch is consistent with a very large, possibly infinite space, but strict proof is out of reach because we always work with a finite sample.
So even with zero curvature, infinity isn't automatic. Why not just declare the universe is infinite until proven otherwise?
Because data discipline matters. We infer global properties from a finite volume, and we have to respect cosmic variance. We see one realization of a universe, not an ensemble of copies. Not seeing an edge within the visible region is a strong hint, not a logical proof. That's why cosmology prizes independent checks. If space were compact on scales comparable to what we observe, we'd expect telltale correlations in the microwave background or clusters of gravitational lenses showing multiple images of the same distant structures, and we don't see those. That doesn't close the case forever, but it pushes compact models far into the corner.
Where does expansion fit in? People hear that galaxies recede faster than light and conclude relativity must be broken.
That confusion mixes 2 different speeds. In special relativity, speed is local, measured in one place with a ruler and a clock. Cosmic expansion describes a change in the metric itself, how we measure distances, and it can make the distance between very far objects grow by more than 1 light-year per year, even though no rocket locally breaks the limit. Think of dots of paint on a balloon as it inflates. The dots don't slide over the rubber, yet the distance between them increases. That's why a radius of 46 billion light-years doesn't contradict an age of about 13.8 billion years. Photons traveled on a road that was stretching under their feet. Once you accept that, the faster-than-light paradoxes evaporate. Nothing is outrunning light, the ruler is changing.
One more common sense edge case. If space is expanding, can the infinite become even more infinite? Or is there a neat mathematical caveat here?
Math stays calm. An infinite set of points remains infinite even if separations grow. For cosmology, the key isn't a raw size number, but the geometry and dynamics of the metric. How fast the scale factor changes, how density fluctuations behave, how gravity and vacuum energy share control of the evolution. Against that backdrop, infinite versus very, very large but finite turns from metaphysics into a technical question. Which observable correlations could let us tell them apart? The most honest summary today is, within our reach, space looks enormous, close to flat, and statistically homogeneous on large scales. Infinity fits the data about as well as the alternatives, but remains an assumption because the horizon puts an unavoidable ceiling on proof.
And just to set the tone right, when people say the farthest stars are practically next door, it's not poetry replacing science. It's a reminder that even billions of light years are tiny compared to a potential infinity. Rhetoric allowed only as an invitation to think, not as an argument.
Exactly. And it's a good cue to recall how we built our sense of scale. Spectroscopy taught us to measure redshift. Standard candles like Type 1a supernovae calibrated distance. CMB maps gave us benchmark angular scales of acoustic peaks. And large-scale structure showed that on hundreds of millions of light-years the universe behaves like a nearly uniform medium with a faint ripple in density. Put together, it's a coherent picture. The world is not just vast, it's dynamic, and we see it as far as age and light speed allow. The infinity question is one of those rare cases where honest science can say possibly yes, and in the same breath, show me.
Which sets up the next step nicely. If the universe is that big, and on average that uniform, where does its staggering complexity come from? Galaxies, clusters, and the cosmic web. And why are we so confident talking about billions of island universes rather than dozens? Let's unpack the evidence and the instruments that gave us that confidence.
When we say billions of galaxies, it sounds like hyperbole. Yet you insist it's a strict conclusion from observations. Where does the proof of such diversity and complexity actually begin?
It starts with learning to see deeper and finer. Once telescopes could gather more light and split it into spectra, we could tell apart nebulae inside the Milky Way from entire stellar systems far beyond it. Spectroscopy showed that many of those nebulae had element lines shifted to the red, and the shift grows with distance. That's not cosmetic, it's a distance ruler in an expanding universe. Then basic statistics kicks in. If a tiny patch of sky contains a certain density of galaxies across brightness levels, we sum over many such patches across the whole sky, account for instrument sensitivity, and estimate the total count. With each deeper look, from the first deep fields to ultra-long exposures with space telescopes, the tally keeps moving toward there are more than we thought yesterday. Hence, billions and likely far more. Not poetic exaggeration, just careful integration of what's actually seen, plus corrections for what's still too faint to catch today.
What exactly are we not seeing right now, and why does it matter for the galaxy census?
Our worst enemy is surface brightness, light spread over area. Distant, low-mass galaxies are often not just faint, but fuzzy. Their light is diluted against the sky background and sinks into noise. Every catalog, therefore, has an invisibility threshold, below which the real cosmos keeps going while our tables do not. When we extrapolate the curves of objects per unit sky area versus brightness, the contribution hiding below that threshold can be significant. Early deep images showed a sea of tiny systems per square degree. Newer data strengthened that. As sensitivity and processing improve, more small, young, odd galaxies pop out. They're exactly what swells the counts from billions to hundreds of billions, and possibly more.
But sheer numbers are just the start. How does that disjointed zoo become the cosmic web, with filaments, nodes, and voids? Why that structure?
Because gravity collects whatever it can, seeded by tiny early universe ripples. Picture nearly uniform dough with a slight ripple in density. Within it, there's an invisible scaffold, dark matter, which barely interacts with light, doesn't shed energy by colliding, and quickly forms gravitational wells. Ordinary gas falls into those wells, compresses, cools, ignites stars. Meanwhile, shocks and radiation from young stars and black holes stir the gas back up. Over billions of years, you get hierarchy. Small galactic seeds merge into larger ones, line up along filaments. Filaments feed nodes, clusters of galaxies, and voids sit between. Numerical simulations reproduce this big picture. We dial the initial conditions, dark matter fraction, baryon density, expansion history, and watch what kind of web forms. The sky's statistics, galaxy separations, mass distributions, morphologies, velocities, match those outputs well. So the core ingredients of the recipe look right.
You mentioned initial seeds. Where do those ripples in an almost uniform medium come from? And how do we measure them today?
Roll back to a very early epoch when the universe was a hot, dense plasma. It carried acoustic waves, real sound-like oscillations where gravity tried to compress and radiation pressure pushed back. When the plasma cooled and photons decoupled from matter, the imprint of those waves froze into the cosmic microwave background as tiny temperature variations and characteristic angular scales. The same oscillations left traces in today's galaxy distribution, the baryon acoustic oscillations. In the spatial statistics, you see a gentle preference for a specific scale. It's the same ruler, carried from the universe's infancy to the adult sky map. By cross-checking the early time and late time rulers, we stitch together the history of structure growth, from micro ripples to the cosmic web.
Galaxies come as spirals, ellipticals, dwarf irregulars, ultra-diffuse, plus a dozen exotic classes. How does that variety arise if everyone plays with the same atoms and the same gravity?
From assembly history and local environment. Grow quietly by sipping gas, and you have time to form an orderly rotating disk with stars on neat orbits, spirals. March through frequent, especially major mergers, and you scramble orbits, heat or expel gas, quench star formation, and end up an elliptical, massive, red, gas-poor, elderly. In dense regions, like cluster cores, tides and hot intracluster medium strip dwarfs into diffuse smudges. In emptier regions, tiny galaxies can live alone longer, keep gas, and churn out young stars. Internal feedback matters too. Supernovae and active nuclei winds switch star formation off, on, or somewhere in between. One set of laws, many outcomes, because initial conditions and neighborhoods differ.
Back to how many are there? Given all the selection effects, surface brightness losses, and more,
How reliable is the jump from what we see to what's really out there?
That's the honesty test. The standard workflow: take deep fields with tens of thousands of objects, build distributions over brightness and size, model what fraction falls below detection at given noise and resolution, add physical priors, e.g., how the small galaxy fraction evolved early on, and integrate. In parallel, compare against cosmological simulations where the true population is known, and then pass it through an instrumental model to see how much a real telescope would recover. If the blinded simulation reproduces the sky statistics, you can trust the extrapolation, cautiously. Hence the phrasing, we're confident about hundreds of billions, and we leave room above, because lower thresholds are tricky and nature loves fat-tail surprises.
Why does billions of galaxies matter beyond the obvious wow factor? What does it change in the big cosmology picture?
Almost everything. The number and types of galaxies set how many stars and planets form, how fast the interstellar medium enriches with heavy elements, how quickly supermassive black holes grow and feed, and how much ionizing light lit up the universe after the Dark Ages. On fundamentals, galaxy statistics tug threads tied to dark matter density, the equation of state of dark energy, and the amplitude of initial fluctuations. Even debates over today's expansion rate, the different values of the Hubble constant, run through distance calibrations and standard candles that live in galaxies. In short, the galaxy count isn't stamp collecting. It's the spine of cosmological inference.
And the comments always ask, if there are so many, why don't we see them everywhere with the naked eye? Where is the boundary between human perception and the sky's real depth?
It's where the eye's integration time ends and long exposures begin. Your unaided eye gathers light for fractions of a second with a small aperture, so you see only the brightest, thousands of Milky Way stars, and in ideal conditions, Andromeda as a smudge. A telescope-mounted camera can stack photons for hours and days without fatigue and suppress noise your eye would amplify. Hence the empty versus overcrowded sky impression. Same sky, different photon budgets and depths.
Let's bridge to the next chapter. We've established that the universe is vast and web-like, that galaxies are receding, and that we have a statistical portrait of their zoo. Next, we need to explain how distances between faraway objects can grow as if nothing limits the speed without breaking any laws. From observations, let's step to the metric, to inflation, and to what it really means when we say space itself expands.
People hear the phrase space itself expands and treat it like a poetic flourish. Yet you insist it's a technical term. What exactly does expansion mean, and how is it different from galaxies flying through empty space?
The point is we don't describe the universe as objects moving across a fixed stage. The stage itself changes scale. In cosmology, we use co-moving coordinates, a grid that stretches with the expansion. So each galaxy sits at a fixed grid point while the scale factor multiplies the distance between grid lines. When we say space expands, we mean that scale factor grows with cosmic time. Galaxies aren't bullets. They mostly rest in their co-moving spots, while the ruler we use to measure distances gets longer. That's why very distant galaxies can appear to separate faster than light without breaking relativity. The speed of light limits local motion through space, not how fast the metric, the distance scale itself, can change over enormous spans. Think of paint dots on a balloon. The dots don't slide, but the spacing increases, and the farther apart they are, the faster their separation grows.
Sounds like a clever ruler trick. Then why don't we see expansion locally? Why aren't atoms or the solar system getting bigger?
Because expansion is incredibly weak compared to local binding forces, and it only shows up where gravity fails to hold things together. Where electromagnetism binds atoms, the nuclear force binds nuclei, or gravity binds stars and galaxies, those systems pin down the geometry and the changing scale factor can't stretch their orbits. On intergalactic scales, there's no single binding to resist the metric's growth, so that's where expansion matters. This also explains the Hubble-Lemaitre law. Recession speed is proportional to distance. Local ties win at small scales, the growing scale factor wins at large ones.
Back to faster than light. People hear somewhere recession exceeds c and conclude special relativity is broken. How do you phrase it so there's no loophole for confusion?
Distinguish two ideas: local velocity through space versus the rate at which distance increases because the metric changes. Relativity restricts the first. No particle or signal outruns light locally, in a region small enough to be nearly flat. When we say a distant galaxy recedes faster than c, we're not describing a flight, we're describing the ruler's growth, which can yield any number at large enough distances. Even light already en route rides a stretching road. At first, it can be dragged away because the road lengthens faster than it advances, and later, when the expansion history shifts, it can gain ground and still arrive. The clean way to see it is with light cone diagrams in an expanding universe. Causal boundaries depend on the whole history of the scale factor, not a single speed.
Now the word inflation shows up everywhere, sometimes even more than Big Bang. What do physicists mean by inflation, and why introduce it at all?
Inflation is the hypothesis that the very early universe went through a period of extremely rapid, nearly exponential growth of the scale factor. It wasn't proposed for drama. It elegantly solves several technical problems. First, the horizon problem. Why the microwave background has nearly the same temperature in directions that at first glance could never have equilibrated. Inflation says those regions were once close together before the blow-up, had time to smooth out, then were whisked far apart. Second, the flatness problem. Why large-scale curvature is so tiny. Exponential growth irons out any initial curvature, like a hot iron flattening wrinkles. Third, unwanted relics, for example magnetic monopoles in some theories, get diluted to invisibility. Mechanistically, you model it with a field, an inflaton, rolling slowly down its potential, keeping the energy density almost constant. When the roll speeds up, inflation ends, the field's energy dumps into hot particles and photons, and the hot Big Bang phase begins. This handoff is reheating. In that language, inflation is not magic, it's concrete field and metric dynamics.
But inflation is still a hypothesis. What observational fallout does it predict that we can actually test?
It makes testable predictions. That's the appeal. Quantum fluctuations of the inflaton get blown up to cosmic scales and become seeds for later density variations. That yields an almost but not perfectly scale-invariant spectrum, which shows up in the microwave background's angular patterns and in galaxy statistics. The characteristic comb of peaks and troughs in the CMB asymmetry spectrum, a slight tilt away from exactly scale invariant, and the scale of baryon oscillations all fit the story. Fluctuations were born very early and then grew. A Boulder signature is a background of primordial gravitational waves that would leave a specific polarization pattern. That search is hard, signals are tiny, and galactic dust is pesky, so the test remains open, but it's powerful precisely because different inflationary dynamics predict different polarization fingerprints.
People often confuse inflation with dark energy because both involve accelerated expansion. Where's the boundary between them?
They differ in era, physics, and scale. Inflation is a very early universe episode at vastly higher energies, typically modeled with a specific scalar field's dynamics. Dark energy is what we infer from much later time observations, showing the expansion re-accelerating under very different conditions. Phenomenologically like a non-zero vacuum energy or something acting close to a cosmological constant. Same word, acceleration, two very different plays. a baby picture and an adult portrait of the same universe, with different actors and costumes.
Back to everyday intuition. If everything is expanding, was there a moment it started? And can we even ask what was before?
It's a fair question about the limits of our equations. Track back through the hot phase, and densities and temperatures soar until quantum effects of gravity should matter, and we don't yet have a finished theory for that regime. Inflation often gets spliced in before the hot phase, but by itself it doesn't license us to speak of a human-style sequence of seconds before it. It may be that time as a global axis is a property of our cosmic phase. Some models make before meaningless, like asking what's north of the North Pole. Others allow a prehistory, from quantum tunneling out of another phase to cyclic pictures. The key is linguistic discipline. When we say beginning, we often smuggle in everyday intuitions physics may not share.
Then here's the interim summary. Expansion means the scale factor grows, the ruler changes. Faster than light in cosmology refers to the metric's growth, not a flight. Inflation isn't a buzzword, but a tool for specific early universe problems. And before is a question for a future quantum theory, not a calendar. What's the natural next step?
Naturally, we should ask what we mean by Big Bang and why it's not a bomb in empty space, but a label for a hot, dense state and its aftermath. From there, we can cleanly discuss whether before is even meaningful, what the competing scenarios are, and the right language to compare them. That's the bridge to the next segment.
When we say Big Bang, people almost automatically picture a bomb going off in empty space. Then they ask what happened before that, where the blast point was, and why anything started at all. How do we unpack those questions correctly, keep the physics intact, and avoid sliding into metaphors?
First thing to lock in. In modern cosmology, the Big Bang is not a detonation inside pre-existing space. There wasn't a cold external vacuum, no surrounding stage, no pre-marked coordinates for debris to fly through. The term refers to a state of extremely high density and temperature from which the universe transitioned into an expanding hot plasma. Elementary particles, then nuclei, atoms, and hundreds of millions of years later, stars and galaxies. We know this hot phase really happened because we see three independent lines of evidence: the cosmic microwave background, with its specific temperature and angular patterns, the abundances of light elements matching primordial nucleosynthesis calculations, and expansion itself, measured spectroscopically. These agree so well that the early hot universe is the working foundation. But if you push the equations further back to higher energies, you hit a wall. General relativity predicts a singularity, a point where curvature blows up and familiar quantities lose meaning. That's not reality ends, it's this theory's applicability ends. So what was before morphs into a question about which physics describes the regime where quantum effects of gravity matter as much as geometry.
So the honest answer isn't before X happened, but our working equations run out, and the next step is to discuss candidate theories, not mythology. What serious options are on the table?
A few broad families, each tackling two linked issues: whether time itself has a beginning, and how the hot phase got its initial conditions. One line says the very notion of time ceases to be meaningful, so before is as ill-posed as north of the North Pole. In this spirit are quantum cosmology ideas like the no-boundary proposal, where the early universe is described not by a classical path from A to B, but by a quantum amplitude for entire geometries. Think of the past being smoothed out rather than ending in a sharp tip. A second line gives the hot phase a prehistory, a prior regime that either smoldered slowly, underwent a compressed phase, or lived in a vacuum with different properties. Here, you meet cyclic or bounce models, where a singularity is replaced by a minimum size and then re-expansion. In some loop quantum gravity approaches, quantum corrections make gravity effectively repulsive at extreme densities, enabling a bounce. Ekpyrotic scenarios, meanwhile, birth our hot universe from a collision of deeper branes or layers. Before belongs to a very different geometry, not our familiar 3D space with a single time. There are also emergent or steady-state prehistories, where the universe lingers in a quasi-steady state for a long time and only later transitions to expansion. So, before is a long, quiet prelude. Finally, in some pictures, the early inflationary phase itself nucleates from nothing in a quantum sense, not from a geometric point, but from a field fluctuation at a specific energy, and that phase sets the initial conditions for the hot episode.
How do we tell elegant philosophy from physics when each sounds like a coherent story? What do observations say, and what can we even hope to test?
Same criterion as always. A theory must unpack into predictions for observables with numbers we can check independently. For the early universe, that means the primordial perturbation spectrum and its slight departures from perfect scale invariance, CMB polarization properties, possible primordial gravitational waves, and large-scale correlations in galaxy maps that retain memory of the universe's childhood. Some scenarios predict detectable tensor signals, some say they should be absent, some allow distinctive non-Gaussian fingerprints to hunt for. We already know the early universe was astonishingly smooth, but not perfectly, just as you'd expect from tiny quantum fluctuations stretched to huge scales. We're confident the hot phase happened because multiple tests converge, but distinguishing a smooth beginning without time, a bounce, a brane collision, or quantum nucleation is right at today's limits. Better CMB polarization maps, ultra-faint gravitational wave searches, and deeper surveys will rule out entire model classes, but there's no guarantee nature left us an easy-to-read tag from the first instant.
People bristle at before had no meaning because our language is linear, earlier, later. How do you say that carefully without sounding like a word game?
Like this. In physics, time isn't handed down from the outside. It's a parameter that appears in the equations for a given system, and in extreme regimes, those equations can change so that a global time axis loses meaning. We see an echo of this in simpler contexts. In thermodynamics, the arrow of time emerges statistically from many particles. Drop to the micro-world of a single atom, and your beloved past-future vector loses bite. In early cosmology, we're not talking psychology, we're asking whether one can consistently extend the coordinate t through a domain where quantum fluctuations of geometry are so wild that notions like distance and angle break down. If you cannot extend it, then what was before is indeed ill-posed. If you can, within a new theory, you can ask about the prehistory's properties and how our observed settings, density, composition, perturbation spectrum, flow from it. Popular books often pair Big Bang and inflation, and readers think inflation is the bang with a fancy label. How do we separate them cleanly? Say it like this. Inflation is a possible pre-hot phase episode where the scale factor grows extraordinarily fast, while the energy density stays nearly constant, smoothing temperatures, flattening curvature, and diluting unwanted relics. Then the inflatant energy dumps into a hot plasma, and the familiar evolution begins with nucleosynthesis and recombination. In that framing, Big Bang isn't a single tick. It's the whole early hot era, including the end of inflation and the subsequent reheating. Inflation is the preparatory act explaining the hot phase's tidy initial conditions. Big Bang names the hot play, not a lone bang.
One last, narrow but important point. If time was born with the universe, does it make the question of a cause meaningless, since causality needs time?
This is subtle because everyday cause is tied to a sequence of events, while in fundamental physics, Causality lives in the space-time structure, light cones determining which events can influence which without violating signal speed limits. If global time doesn't exist across some region, then everyday causality has no arena to operate in there. That doesn't kill more abstract why this, not that explanations via properties of the equations or the space of allowed states, but that's not A caused B 1 second before t equals 0. So the careful statement is, the why question remains physically meaningful, but it doesn't need to be phrased as event A produced event B just before 0, because the very scale of seconds may have emerged with the regime we call our universe.
So the bundle is Big Bang, not a bomb in a void, but an early hot phase with concrete observables. Before is a question for a future or extended theory that treats gravity quantum mechanically. And until such a theory arrives with testable predictions, we keep several tidy scenarios on the table, distinguished not by pretty metaphors, but by the signals they ought to leave in the sky. Which leads naturally to the place where these scenarios collide with imagination. Can new worlds be born from early fluctuations, from vacuum phases, or from extreme objects like black holes? Let's sort what physics truly permits from what's only a beautiful metaphor.
When people ask, how are new universes born, they usually imagine some giant explosion happening off to the side of ours. In real cosmology, what are you talking about when you say universe formation?
We don't mean a factory stamping out worlds on a conveyor belt. We mean scenarios where the underlying medium of the universe can change state, and with it, the effective laws and constants. The most discussed mechanism is eternal inflation. The idea is this. In the very early universe, the energy density was governed by a special field. If that field doesn't roll down to its minimum everywhere at the same rate, you get regions where expansion stays nearly exponential, like yeast dough rising, while other regions end inflation, convert that energy into a hot plasma, and begin a normal Big Bang-style history. Because the inflating region itself grows faster than new bubbles can finish and thermalize, the overall process never dies out. Somewhere inflation keeps going, elsewhere stars and galaxies are already forming. From inside a bubble, you see your own cosmic horizon and your own history, and you never see the inflating background sea, not because it isn't there, but because light from it can't reach you in principle.
You keep saying bubble. Nice image, but what is it physically, and what does a different state of the medium mean?
Think phase transitions. Water can be ice, liquid, or vapor, switching abruptly under the right conditions. In field theory, the vacuum isn't empty, it's the lowest energy state, and the landscape of a theory can have multiple minima, different vacua. If the system sits in a false vacuum, not the deepest minimum, it can quantum tunnel to a lower one. In cosmology, that looks like the birth of a tiny bubble of the new vacuum that then expands at near light speed. The pressure difference across the wall releases huge energy. Inside the bubble, parameters change, the tuning knobs of physics, characteristic energy density, expansion rate, particle content. Reheating then happens inside. Vacuum energy turns into ordinary particles and photons, and the familiar hot phase begins. Different bubbles can inherit different parameters, so the equations themselves allow a variety of local universes within a big multi-scenario.
If different bubbles can have different knobs, we run into the dreaded anthropic principle people use as a fig leaf for ignorance. Do we actually need it here?
Used strictly, it's not "we got lucky, the end." It's a statement about conditional probability. Among all bubbles with different parameters, observers will find themselves in those that permit long-lived stars, stable chemistry, and enough time for complexity. It isn't a causal "why this exact value," it's a selection filter. Ideally, you pair it with hard predictions, say how often bubble collisions should occur and what subtle marks they'd leave in the microwave background. If we found such a signature, the conversation would move from philosophy to observational cosmology.
About those bubble collisions. Sounds cinematic. What, if anything, could we actually see, and why haven't we?
If two bubbles nucleate not too far apart and their expanding fronts intersect, a sky map for an observer inside one bubble could show a circular or oval patch whose microwave background statistics are off. Slightly different temperature, correlation structure, and a specific polarization pattern. People have hunted these with anomaly finding algorithms, and so far there's no convincing detection. That's not defeat. It tightens the bounds. If collisions happen, they're rare, or their imprint is weak and buried in astrophysical foregrounds. Next-generation polarization maps will keep up the search.
You keep talking about vacuum, landscape, multiple minima. Where does this landscape come from? And are we just playing with words without a single fundamental theory?
That skepticism is fair. Landscape is a metaphor for the many low-energy states allowed by some candidate unifying theories, frameworks with many fields and symmetries. We truly don't know which big project, string constructions, loop quantum gravity, or something else will survive. So the landscape isn't a finished atlas, it's a working idea. If fundamental physics allows more than one stable vacuum, cosmology naturally supplies mechanisms to transition between them. That's enough to motivate a many bubbles, many worlds picture without committing to a specific theory underneath. Our honesty check stays the same. Can we link that general picture to measurable statistics and, in principle, to testable fallout?
Since we're among rarefied theories, what about the harder-edged favorite of science fiction, new universes born inside black holes? Is that part of this story or something entirely different?
Adjacent but distinct, and it's our next segment. Short version, general relativity's equations do admit solutions that mathematically can be read as bridges between geometries, and there are scenarios where collapse to a black hole could, under extreme assumptions, stitch to an expanding region beyond. But the stability of those solutions in a messy, non-ideal universe and the need for exotic matter are major roadblocks. So it's cleaner to give black hole nurseries their own chapter and separate what's mathematically elegant from what's physically doubtful.
Back to eternal inflation. If it's eternal, don't we hit paradoxes with an infinite set of worlds where anything that can happen will happen, and statistics lose meaning?
That's the measure problem. How to assign probabilities in an endless hierarchy of bubbles, with new ones forming somewhere at every finite time. Different ways to cut off infinity yield different answers, unpleasant but honest. Practically, we look for observables weakly dependent on the measure, and we design local tests that don't need global statistics. Analogy, standing on a beach, you don't need to count every wave on Earth to predict the next dozen. Local data suffice. In multi-scenarios, we try to play the same game. Extract locally testable predictions and leave the philosophy of infinity to philosophers.
Give me a crisp bottom line. Stripped of shiny words, what would you stake as the summary of how new universes are born?
Here it is. If an early universe field drove inflation and its dynamics let different regions end that phase asynchronously, then eternal inflation naturally yields bubbles in which the hot phase starts and an independent cosmic history unfolds. If fundamental physics truly allows multiple stable vacua, different bubbles inherit different settings, and we get a multi-scenario where our parameters aren't unique, just compatible with long-lived, complex chemistry. This approach has observational consequences, subtle statistical fingerprints in the early radiation, and potential traces of bubble collisions, and those can be searched for. Everything else is imagery and philosophy that cannot substitute for data.
And that's a clean springboard to the next topic. Even if general relativity's math admits bridges and inside-out solutions, can we honestly call black holes portals to new worlds? Or is this where a beautiful blueprint doesn't survive real physics?
The phrase, a black hole is a portal to another universe, is so tempting it's hard to let go of. If we set the movies aside, on what basis do physicists even talk about bridges and exits?
On the basis of general relativity's math. Its equations admit bridge-like solutions. First, the non-stationary Einstein-Rosen bridge, later, the neatly written Morris-Thorne wormholes. On paper, they connect two spacetime regions, even two distinct cosmoses. In classical form, though, such a bridge collapses instantly. You can't traverse it. To hold the throat open, you'd need matter with effective negative energy density, i.e. violations of the usual energy conditions. Local quantum effects can mimic that. Think Casimir-type setups, but scaling it to an engineering-level tunnel is about as likely as walking to Andromeda. Bottom line, the equations don't forbid bridges. Nature hasn't shown us the material or the build plan.
What about white holes, the reverse of black holes? People say, entry here, exit there.
A white hole is a mathematical time reverse, a region nothing can enter, only exit. In idealized extensions of GR solutions, a black plus white pair can exist. The trouble is instability. Tiny perturbations turn a white hole into a mess of singular behavior. Contact with real matter kills it. We see no persuasive evidence for white holes, and astrophysics explains high energies and jets without invoking them.
Common reply is, okay, static bridges are unstable, but maybe spin helps. Real black holes rotate.
Rotating geometry, Kerr metric, is richer. An ergosphere, inner horizons, even a ring singularity and apparent passages in the classical picture. But that elegance is fragile. The interior suffers mass inflation. Microscopic disturbances grow catastrophically, wrecking those tidy corridors. Add real plasma, magnetic fields, and accretion, and the classical shortcuts become physically impassable. Spin buys us relativistic jets and frame dragging, not a turnstile to another cosmos.
So the portal fails on stability. What about causality? Wouldn't a traversable wormhole create paradoxes?
Exactly. A traversable wormhole can be turned into a time machine by moving its mouths just so. Then come closed time-like curves, grandfather paradoxes, and other headaches. Many physicists suspect quantum effects would crank up the energy near the throat and destroy the tunnel, so-called chronology protection. Pretty, but effectively another no-go. The universe bolts shut what would otherwise break global consistency.
How about beyond GR? Some say a black hole could spawn a baby universe, a new expanding region.
Those ideas exist, from Smolin's cosmic natural selection, new universes budding from collapses, to quantum bounces in some loop quantum gravity-style models, or collapse morphing into a white hole-like phase. The logic changes, not go through, but form a causally separate region behind the horizon. For us, that's not a portal, no signals return. For there, it's a real world, with its own time and arrow. Same problem, no evidence, murky observables. Even if children exist, the parents can't learn about them.
But we do see powerful jets, bright emission, flares. Isn't that leakage from a portal?
No, jets are magnetodynamics in the disk and near the horizon. Hole and disk rotation winds up magnetic fields, flinging plasma along the spin axis at relativistic speed. All of that happens outside the horizon. Inside is radio silence by definition. Geometry forbids outbound signals. In the popular picture, a black hole spits stuff out. The error is simple. It's the disk and fields doing the spitting.
Suppose we try to prop a wormhole open with exotic matter. In theory, it's possible. What stops us?
Two roadblocks. First, energy. You'd need sustained, macroscopic violations of the null energy condition, for a long time. Quantum effects provide tiny negative energy dribbles, nowhere near enough to brace a throat under astronomical stress. Second, noise. Even a perfect tunnel would be battered by infalling particles, gravitational waves, and field fluctuations, driving it unstable. It's like building a house of cards on a runway.
So then give me the strict answer. In any rigorous sense, can black holes be called portals?
Strictly, no. If portal means a traversable path that transmits information or matter from our exterior universe to elsewhere and back. A black hole is a causal trap. In, yes. Out, no. In broader, speculative frameworks, you can talk about birth of causally separate regions or mathematical bridges, but that isn't a portal in the everyday sense, and not a communications channel. Different geometries, not a pipeline.
So why does the portal idea live on despite all these strikes against it?
Because it's a beautiful myth that promises two human dreams, escape and contact. And the equations do sketch bridges, so the myth has a mathematical shadow. But science is where beauty meets reality. Once you add stability, quantum corrections, plasma, radiation, and causality, the bridges fold. What remains is humbler and sturdier. Black holes are our best laboratories for extreme curvature and energy, not doors.
Leave listeners with one honest line. How would it read?
Like this: general relativity lets you draw bridges. Physics makes them non-traversable. Spin gives jets, not exits. Any baby universes, if they exist, are causally sealed. Observed astrophysics works fine without portals. Let screenwriters keep the romance. We'll keep measuring shadows, stellar orbits, and gravitational waves, the things that tell the truth about black holes.
The phrase, when physics doesn't work, sounds scary. What should we honestly take that to mean? Does reality break, or do our equations just leave their comfort zone?
It's our descriptions that fail, not the world. Any theory is a map with a scale, assumptions, and a domain of validity. Classical mechanics is excellent for apples and satellites, but it won't give precision answers for atoms. General relativity nails planetary gravity and binary pulsars, but if you keep pushing it into cosmological or black hole singularities, it spits out infinities. That's the map telling you, beyond this point, use new variables and different physics. Nature isn't breaking, our map is out of range.
Where exactly is that boundary for gravity? At what point do Einstein's equations stop being trustworthy?
Where quantum fluctuations of the fields and of geometry itself rival the classical values. The guideposts are Planck scales, lengths around 10 to the minus 35 meters, and times around 10 to the minus 43 seconds. There, the smooth fabric of spacetime isn't smooth. Geometry stops being background and becomes a quantum player. In that regime, GR, fundamentally a classical theory of continuous geometry, can't apply without quantum corrections. Likewise, quantum field theory on a fixed background doesn't know what to do when the background itself fluctuates. Bottom line, we need a quantum theory of gravity. We have candidates and effective approximations, but no universally accepted single language for all regimes.
So, doesn't work really means we're using the wrong scale map. Can you give a down-to-earth case where the theory is right, but the model choice makes predictions meaningless?
Turbulence. The fluid equations are correct, but nonlinear dynamics makes exact long-time forecasts for a specific turbulent jet basically impossible. We switch to statistics, means, spectra, because that's the right map for that question. Cosmology is similar. We predict the large-scale structure with correlations and power spectra, not the coordinates of every galaxy 10 billion years from now. The theory didn't break, the question style did.
Back to black holes. People say that at the event horizon, the laws stop working. Is that accurate?
No. Near the horizon, classical physics is fine. For a freely falling observer into a massive hole, local physics looks ordinary. Tidal forces are small. Trouble starts deeper in when you try to square three things: Hawking radiation, a smooth horizon, and information conservation. Their internal logic pull in different directions. That's the information paradox and the debate over firewalls. Add the trans-Planckian problem. Quanta we see far away seem to originate from modes of absurdly high frequencies near the horizon, and the classical picture creaks. That's not laws disappearing. It's us lacking the right quantum gravity formulation to make all the pieces coexist cleanly.
And the singularity inside isn't creaking, it's a brick wall. What exactly fails there?
A singularity flags that geometric quantities like curvature diverge in finite proper time for an infalling observer. Physically, that means the smooth metric description loses meaning before we can re-express it in better variables. In a good theory, infinities should go away, as ultraviolet infinities did in quantum electrodynamics after proper renormalization. For now, the honest stance is, inside the horizon, classical evolution leads to a region where our theory goes silent. We don't yet know whether quantum gravity smooths that sharp corner into a bridge, a bounce, or something else.
Beyond extreme densities, where else do familiar descriptions fail?
Two situations. First, when you demand answers a theory wasn't built to give at that scale or under those assumptions, like applying ideal cosmic homogeneity to galaxy-sized patches and then being shocked that disk-star dynamics don't match. Second, when you ignore the role of observer and measurement in quantum theory and try to port classical causality and trajectories straight into regimes dominated by superposition and decoherence. In both, blame the question, not the universe.
So, what tools do we have right now to hold the line at the frontier without drifting into sci-fi?
Effective theories and observational anchors. Effective theory says, be honest about energy and scale. Write down every symmetry allowed term and improve predictions systematically without pretending we know the ultimate theory. That's how we succeed in condensed matter physics and partly in early universe cosmology and black hole astrophysics. Observational anchors are gold standard systems. Binary pulsars, gravitational wave mergers of black holes and neutron stars, black hole shadows, and CMB maps. They won't tell us what's inside the singularity, but they force any new theory to match numbers we've already measured, a great vaccine against pretty but empty speculation.
What about lab stand-ins? Can we play quantum gravity analogs on Earth at all?
There's analog gravity, superfluids, optical waveguides, Bose-Einstein condensates where wave dynamics mimic fields on an effective metrip, even analogs of Hawking radiation. It's not quantum gravity, just math with similar structure. But it's useful. It trains intuition and tests signal extraction methods in noisy data. Just don't over-transfer the conclusions to astrophysics. An analog is a trainer, not the actual mountain.
Give me one clean sentence. When is it fair to say, physics doesn't work here?
Never. The fair phrasing is, this model's applicability ends here. For black holes, that means at the horizon, GR plus quantum field theory deliver testable, confirmed effects, lensing, orbits, shadows, accretion dynamics. Closer to the singularity, and in the very early universe, we lack a consistent quantum gravity, so claims about the very center or the first instant are hypotheses. That's not the end of science. It's a signpost for where to point the next telescope and the next equation.
Perfect. We've marked the edges of the map without blaming the ocean for being deeper than our ruler. So next up is the practical question.
What actually happens to a real body that falls into a black hole? What does an external observer see? What does the falling one feel? And how far do the solid equations take us before assumptions take over?
When people ask, what happens if you fall into a black hole, they expect one flashy answer. You say there are at least two distinct scenarios, a stellar mass black hole and a supermassive one at a galactic center. Let's start with the differences. Why does mass change the fall so drastically?
Because of tidal forces, the difference in gravity between your head and your feet that stretches you along the inward direction and squeezes you sideways. In a stellar mass black hole, the event horizon radius is small, curvature near the horizon is large, and those tidal gradients become extreme before you even reach the point of no return. Any material, however tough, first feels brutal stretching, loses structural integrity, and devolves into plasma. That's the famous spaghettification. A supermassive black hole behaves the opposite way at the edge. Its horizon is enormous, curvature at the horizon is milder, so the tidal forces at the boundary can be tolerable. A freely falling object only hits the truly violent physics after crossing the horizon, deeper in, where distances to the central region are so small the geometry twists trajectories and the tides ramp up beyond any material strength. So in one case, death comes before the horizon, in the other, after, but either way, the finale is disassembly down to molecules, atoms, and beyond.
Walk us through the fall from two viewpoints, a distant observer with a camera and the falling traveler. What do their clocks and eyes record?
For a distant observer on a stable far orbit, the infalling object appears to slow, its light reddens, and it seems to freeze at the brink. Each successive photon leaves from deeper in the gravitational well, loses more energy climbing out, arrives later and at lower frequency. That's not an optical illusion, it's gravity modifying time and light paths. For the faller, proper time runs normally. There's no eternal wait. Crossing the horizon happens in finite proper time and is uneventful, especially for a supermassive hole where tides at the edge are small. The trouble begins deeper in, where the future light cone tips, so that forward in time is inward in radius, and tidal gradients become unendurable.
Common question, after crossing the horizon, could a powerful transmitter still send anything out?
Categorically, no. By geometry itself. The event horizon isn't a material wall, it's a boundary where all future directed paths lead inward. No causally allowed signal can cross back out. You can gain things up to the last moment before the horizon, transmit at high frequencies, compensate for gravitational redshift, but after the crossing, the light cones are tilted, so there's simply no outward direction to aim a beam. Point of no return is the most honest phrase here.
What's along the road to the horizon? People imagine empty vacuum, but we hear about accretion disks and jets. How harsh is the environment?
Most feeding black holes live inside accretion structures, streams and disks of hot gas and dust. As gas loses angular momentum and falls in, friction and magnetic processes heat it, and it radiates from X-ray to radio. Falling through that environment means intense heating, bombardment by energetic particles, shocks, and fierce radiation. In many regimes, plowing through dense disk layers destroys an object well before the horizon. The clean, free fall in vacuum is a classroom idealization. Astrophysically, the path to the horizon runs through a hostile, hot atmosphere. And jets, they're not matter spat out by the hole. They're plasma accelerated by magnetic fields wound up by rotation in the disk-hole system. An outside phenomenon, not an interior leak.
Now, the dramatic part. Suppose we cross the horizon of a supermassive hole. Tides are still bearable. What happens next? What does the point of no return look like from the inside?
Inside,
Every choice of trajectory still ends in the central region. There's no turnaround burn. Light cones tilt so that moving forward in time forces you inward. That's literal geometry, not metaphor. As you approach the central zone, space-time changes so sharply that any composite structure fails. Radio stretching skyrockets, transverse compression pumps energy into internal degrees of freedom, and everything shreds. For a Kerr rotating hole, you add layers, outer and inner horizons, the ergosphere, frame dragging, but the detailed journey past the inner horizon runs into instabilities. Tiny perturbations amplify mass inflation, and the neat classical pathways toward bridges give way to a more physical picture of chaos and breakdown. Elegant extensions on paper are too fragile for a noisy, field-filled universe.
What does the falling traveler actually feel? How long does the trip take? What happens to vision and temperature? And is there any chance of a quick, unaware end?
Proper time from horizon to center is short. Minutes to hours for supermassive holes, fractions of a second for stellar mass ones. It depends on starting height and momentum, but no one lives long inside. Near and just past the horizon, the sky looks bizarre. The sphere of stars compresses into a bright crown above you, while space behind stretches, gravitational lensing gone wild. In a vacuum idealization, you'd get a spectacular view. In reality, an accretion flow blinds you with radiation long before any postcard moments. Temperature-wise, an empty plunge might keep you cold, but real accretion cooks you, and tides ultimately plasmify matter beyond any meaningful sensations. There isn't a literal instant painless end. Disassembly is finite but brief. A brain could register some of it up to a depth. Beyond that, plasma formation and neural rupture end experience.
What about the information paradox? From the outside, what falls in seems lost, while quantum mechanics demands unitary, information-preserving evolution. Where does that debate stand, and does it change the falling story?
The debate concerns the full life cycle, formation, Hawking evaporation, and any remnant, not the infall stage. For stellar and supermassive holes, Hawking temperatures are tiny, and evaporation times dwarf the age of the universe, so none of this touches our practical experience. Conceptually, though, unitarity says information must survive, while horizon suggests the opposite. Proposals abound, information hidden in subtle correlations in Hawking radiation, or not quite smooth horizons, firewalls, or holographic mechanisms that encode data outside. For our purposes, these are ultra-fine quantum effects on enormous timescales. Your classical plunge and destruction don't depend on which camp wins, even though a future consistent theory must reconcile local geometry with global unitarity.
Two quick clarifications people ask a lot. First, could Hawking radiation burn you on the way in? And second, any non-zero chance of surviving the horizon of a stellar mass hole?
Hawking radiation for astrophysical holes is ridiculously cold. Temperature falls as mass rises. And for supermassive holes, it's below the CMB temperature. You'll be burned by the disk and shocks long before Hawking quantum matter. As for survival in a stellar mass hole, tidal forces at the horizon are so large that structural failure happens before crossing. Even microscopic, ultra-strong probes would exceed deformation and heating limits before sending a hello from below. For supermassive holes, crossing intact is possible, postponing, not avoiding the inevitable deeper in.
So give me the one-sentence reality check. Falling into a black hole isn't a trip to elsewhere. It's a one-way journey with no feedback to the outside universe, where to distant eyes you freeze at the edge, while to yourself you cross quickly and quietly, and then tides and hostile plasma finish the job, leaving only the black hole's own parameters as the stable record. Fair?
Fair. A black hole is not a gateway, it's a geometric trap whose beauty lies in precise equations, not promises of exotic exits. And to be blunt, no plausible technology turns the event horizon into a revolving door because the obstacle is causal geometric, not engineering. Next stop, where many theorists, tired of dead ends, follow the inner beauty of mathematics and symmetry to pick directions, not a substitute for experiments, but a reason new ideas often emerge from structures with repeating harmony.
I often hear that theorists choose directions by mathematical beauty, as if equations must be elegant. To an outsider, that sounds like aesthetics instead of science. What do you actually mean by beauty? And why are symmetries treated like a navigator?
By beauty, we don't mean pretty fonts in a textbook. We mean compactness, symmetry, and internal economy in a law of nature. Historically, those traits led to powerful unifications. Maxwell's equations fused electricity and magnetism into a single field theory. Dirac's equation, insisting on relativistic symmetry and linearity, essentially forced the existence of antiparticles. Gauge symmetries led to the Standard Model, with its SU3 times SU2 times U1, where strong, weak, and electromagnetic forces follow one organizing logic. The key thread is Noether's theorem. Every continuous symmetry yields a conservation law, and vice versa. Conservation laws hint at which symmetries to look for. So when a theorist says, "This is beautiful," they usually mean this is minimal, symmetric, and fruitful. It produces many consequences from a small set of premises.
But nature doesn't have to respect our taste. Were there times when beautiful ideas led nowhere, while ugly details turned out true?
Absolutely, and it's a healthy cold shower. A taste for simplicity pushed the naturalness idea, where non-dimensional numbers shouldn't be absurdly fine-tuned. Yet the cosmological constant looks ridiculously small relative to Planck scales, and beauty hasn't explained that. For years, it seemed ugly to allow neutrino masses, but oscillation experiments proved they have mass, and theory adjusted. The CKM matrix, with a complex and CP-violating phase, once looked like technical grit, but it became central to understanding matter-antimatter differences in decays. Conversely, elegant global supersymmetry promised to cure naturalness headaches, but at current accelerator energies, we see no clear traces. That doesn't kill the concept, but it reminds us aesthetics is a heuristic, not a proof.
So, how do you decide when to trust aesthetics and when to set it aside and obey the data, even if the result is ugly?
We always obey data. Beauty helps pick a direction before the experiment and keeps us from random parameter fishing. But once a measurement appears, there's one criterion. The model must numerically match observations and be replicated by independent groups. Day to day, that looks like build the most symmetric theory you can, then honestly account for the fact that nature's symmetries are broken, spontaneously or explicitly. The Higgs mechanism is exactly that. The equations are symmetric, the vacuum chooses an orientation, and the world gets particle masses. Beauty gives compact rules. Symmetry breaking makes those rules fit reality. Then come the tests, cross-sections, decay spectra, cosmological parameters. If an ugly coefficient preserves agreement with data, we keep it and file the question under why this value. Sometimes, years later, we discover a structure that makes that number natural, and beauty catches up to truth after the fact.
We toss around symmetry like it's a universal talisman. Which symmetries truly guided physics, and which ones distracted?
Gauge symmetries have been the most productive. Demanding local invariance, point by point in spacetime, forces you to introduce carrier fields, which create the interactions. That's how photons, gluons, and W/Z bosons arise. Spacetime symmetries, local Lorentz invariance, and general covariance set the language of relativity and gravity. Insisting the laws look the same to all observers on any smooth coordinate grid leads straight to Einstein's equations. There are also symmetries that are gorgeous mathematically but looser phenomenologically. Expanded group structures for grand unification give elegant pictures, yet specific versions would imply proton decay or fixed patterns of masses and mixing angles we don't observe. Not a death sentence for the idea, but a reminder. Every symmetry must pay its bills with measurements.
Sounds like symmetry alone doesn't do much without a breaking mechanism. Why are broken symmetries so important?
Because a perfectly symmetric world is often too poor to resemble ours. Symmetry is the framework. Breaking is how you fill in the details. Spontaneous breaking is like a magnet picking a direction. The equations are isotropic, but the system chooses an axis and observables appear. In particle physics, the axis is the Higgs vacuum expectation value, giving mass to W, Z, and the fermions. Cosmology mirrors this at large scales. The early universe may have been oversymmetric, then phase transitions chose domains where the same equations hold, but parameters differ. The beauty is that one mechanism explains both order and variety.
People argue over naturalness and fine-tuning. Is it acceptable for a parameter to be insanely small without a deep reason, or is that a red flag? Where do you draw the line?
It's part taste, part discipline, part statistics. Fine-tuning worries us because it makes a theory fragile to input changes. On the other hand, history has parameters that looked unnatural until we uncovered deeper structure. Think the electron charge and renormalization in QED. In cosmology, the tiny cosmological constant is the flagship case. Either it's extreme fine-tuning, or we misunderstand the statistics of possible vacua, or dark energy has another nature. Practically, I won't trash a working model just for an ugly number, but I keep my ears up and look for an experiment that can distinguish ad hoc tuning from hidden structure. Beauty without a test is literature. A test without beauty is engineering. Science happens where they meet.
Can you state a clean rule of thumb you use as a filter when data are still sparse?
Yes, minimality, testability, predictive power. Our minimality, don't add entities you don't need to explain the phenomena. Testability, the theory must yield at least a few quantitative consequences within reach of observations in the foreseeable future. Predictive power, the theory must forbid something, not merely permit everything. Otherwise, it's a glossary, not a theory. Symmetries help with the first. Symmetry breaking helps with the second and third. If a proposal is beautiful but doesn't cut assumptions or deliver hard tests, it's a good preprint but a weak compass.
So, what's the value of talking about beauty for a regular listener who cares more about how it works than how elegantly the equations are written?
Beauty is a heuristic that has historically helped us find truth faster than blind search. We shouldn't trust it uncritically, but we should grasp the logic. When the world follows repeating patterns, symmetries are the shortest language for those patterns. If tomorrow we get a theory of time or gravity that's ugly, yet fits all the numbers, we'll accept it, and then most likely we'll find a reformulation that reveals its beauty, because beauty often turns out to be a synonym for consistency and compressibility of description. Not a cult, just a working habit.
Then the segue writes itself. If beauty is about order and symmetry, how does the idea fit that time might not exist as a fundamental substance, that its arrow is statistical, and at the deepest level, the equations are timeless? Let's unpack what physicists mean when they say time doesn't exist and what actually disappears: clocks, causality, or merely a convenient way to order events.
The phrase time doesn't exist sounds like a philosophical trick. What are physicists actually claiming? Our clocks are lying, causality is gone, or we're asking the question the wrong way?
No one's smashing clocks or canceling causality. The point is that the universe has no single global time ticking the same everywhere for everyone. At a fundamental level, you can write the equations with no external time variable at all. You describe the total state, and the ordering of events is recovered from relations between subsystems. In that view, time isn't an outside metronome, it's a way of encoding how some quantities change relative to others. In practice, we build clocks from regular processes, atomic transitions, Earth's rotation, resonators, and compare everything else to them. That's operational, relational time, not a universal alarm clock.
If there's no common time, how does relativity work, where clocks in different places really do tick differently?
Relativity says exactly that there's no universal now. Each observer has proper time, what an ideal clock they carry along their world line would read. Gravity and speed modify that clock rate. Deeper in a gravitational field, it ticks slower. At high velocity, slower again. This isn't philosophy, it's engineering. GPS would fail without constant corrections for orbital speed and altitude. Our everyday tech already lives without global time and with geometry in the loop.
So where does the arrow of time come from, the sense of past to future, if the basic equations are time reversal symmetric?
It's statistical. For big systems, we use coarse, average descriptions. In that language, entropy, the count of microstates compatible with what we observe, almost always increases, because there are vastly more ways to be messy than exquisitely ordered. The early universe began in an exceptionally low entropy state. That unusual beginning sets the direction. Entropy climbs, chemistry runs forward, biology ages cells, memory gets written into the future rather than read from it. In quantum systems, decoherence adds to this. When a system irreversibly entangles with its environment, phases become unobservable, and we get effectively one-way behavior.
And those bold claims that at the fundamental level time doesn't exist, is that wordplay or physics?
It's a careful statement that the fundamental laws can be cast so there's no global T, only constraint equations relating variables. Then you choose one degree of freedom, call it a clock, and express the others in terms of it. That's the relational approach. When the pendulum is at this angle, the field energy is that. And the distance between these events is such and such. In quantum language, you use conditional probabilities. What's the probability the system is in state X, given that the clock reads Y? No psychology here, just math of correlations.
If there's no master clock, does causality suffer? How do we mean A influenced B without a shared calendar?
Causality lives in light cones, not in calendars. Event A can affect B if B lies in A's future light cone, i.e. a signal respecting the speed of light limit can get from A to B. That cone structure is part of space-time itself and doesn't need an external T. Even in timeless formulations, it remains, telling you which correlations are allowed and which are impossible. So causality stays. What's abandoned is a global clock.
People keep asking, what was before the Big Bang? If time as a global axis didn't exist, is the question even meaningful?
It's meaningful as a question about the limits of our equations. If you run the hot Big Bang stage backward, you hit a regime where quantum gravity should matter and our finished theory is missing. In some scenarios, before is ill-posed as north of the North Pole. The time axis is a property of our phase. In others, there is a prehistory, from a bounce to a long, steady prelude. Either way, the key isn't the word before, it's the observables. Patterns in the background radiation, polarization, and any primordial gravitational wave background.
If time is relations, could it vanish in the far future if there are no good clocks left?
More like we'd run out of good clocks. If the universe thins into an ultra-dilute, nearly massless state, few systems provide stable periods or scales. Operationally, you'd switch to dimensionless descriptions, angles, spectral shapes, rather than seconds and meters. Not time turned off, but a change in the coordinates most convenient for description.
What about the block universe idea, where everything already exists, past and future alike? Doesn't that kill freedom and dynamics?
The block view is geometric. The full history is a 4D object, and flow is a property of observers tracing their world lines and slicing out a sequence of nows. It coexists with dynamics and causality just fine. Locally, you have proper time, local equations, and light cones. Questions about freedom are philosophical. Physics speaks about allowed evolutions and probabilities.
Give me one plain sentence. Does time exist?
Like this: the universe has no single cosmic alarm clock. What we call time is the coordinated change of physical quantities relative to others, with local clocks for each observer and an arrow emerging from a low entropy beginning and the statistics of large systems.
Then the natural finale, we've dropped the universal T, kept causality, and understood the arrow. Next step, did nature leave any markers of other worlds? Where do we look for them, and why do we have constraints rather than direct evidence so far?
When we say traces of other universes, it sounds exciting but vague. Where exactly do you look? What counts as an honest signature? And why has no one pointed at the sky and said, there, proof?
Start with the principle. Look where alternative bubbles or other cosmic phases could have left fingerprints in the statistics of our sky. The most sensitive plates are the cosmic microwave background, CMB, and the large-scale structure of matter. For the CMB, there are three classic classes of targets. First, geometric anomalies, circular or oval patches with distinct temperature and polarization statistics, as might arise from bubble collisions in eternal inflation scenarios. Second, departures from statistical isotropy and from clean Gaussian randomness, mild dipole modulations, unusual correlations on the largest angles, specific kinds of non-Gaussianarity. Third, polarization signatures, especially B modes, that could be amplified or distorted by early events, phase transitions, or crossings of domain boundaries. We hunt these methodically, map the sky, comb it with algorithms, and compare against millions of mock skies where anomalies come from pure chance and instrument noise. So far, every candidate either dissolves into statistics or yields to mundane astrophysics like dust and radio sources.
The popular press loves the CMB cold spot. Isn't that the smoking gun?
The cold spot is an intriguing degree-scale cool region relative to the mean. It's tempting because under simple Gaussian models, a dip that deep is rare. But there are standard explanations. A large supervoid along the line of sight can cool passing CMB photons via the integrated Sachs and Wolf effect. And the assessed rarity depends on how you define the anomaly metric, clean the map of dust, and account for the "we looked everywhere" penalty that makes oddities likelier to show up by sheer numbers. Net, a great stress test for pipelines and models, but nowhere near sufficient to declare footprint of a foreign universe.
Beyond CMB maps, where else can we catch such imprints so it's not just the same statistics, in other words?
Several independent routes. First, space-time variation of fundamental constants, especially the fine structure constant, alpha. If distinct vacuum domains had slightly different settings and a domain wall crossed our visible patch, high-precision quasar spectroscopy could reveal tiny line shifts. It's brutally hard and systematics heavy. No convincing signal yet. Second, relics of early universe phase transitions, cosmic strings, textures, Other topological defects would leave knife-edge features, line-like CMB discontinuities, lensing without massive lenses, and bursts in the gravitational wave background. Searches are systematic. So far, it's not detected, bounds tightening. Third, a stochastic gravitational wave background. Violent early events, strong phase transitions, bubble collisions could have pumped long wavelength ripples into spacetime. Pulsar timing arrays, ground detectors, and future space-based observatories can check for excess foam at telltale frequencies. That's a genuinely independent window, because GWs couple weakly to matter and carry a cleaner history.
You keep saying domains and boundaries. What picture is that, without any mysticism?
In field theory, the vacuum isn't empty. It's the lowest energy state, and it can come in multiple phases, like water as ice, liquid, or vapor. If the early universe cooled through phase transitions, it could form domain structures where fields picked different equilibrium values. The interfaces are domain walls. If a domain wall crossed our observable volume, it could slightly shift curvature, tweak local expansion, and nudge the fluctuation spectrum. The catch: long-lived, energetic walls clash with lots of data. They'd break homogeneity too strongly. Realistic models make them rare, thin, and short-lived, which means any imprint is extremely subtle.
Are there hard tests that, if they hit, would leave little room for alternatives?
Two standouts. One is concentric circles with coherent polarization in the CMB, as the signature of a specific bubble collision, a geometrically rigid template. If both temperature and polarization line up, there aren't many escape hatches. Two is spectral and angular features in the gravitational wave background, matching first or second order phase transitions at definite temperatures. The spectrum's shape and peak frequency are tied to the physics. Detect that with a future space GW mission, and then stitch it to CMB and large-scale structure data, and you have a joint picture where a multiverse-style scenario becomes working cosmology, not armchair philosophy.
If the tests are that sharp, why don't we have an answer after decades of maps and thousands of papers?
Because nature is stingy with labels and our instruments are finite. On the largest angular scales, the CMB has only a few dozen statistically independent modes. Cosmic variation is huge. On small scales, foregrounds, dust, synchrotron, sources get in the way. Any claimed anomaly has to survive everything: sky masks, different foreground cleanings, alternative pipelines, and independent data sets. Most effects fade as the tests harden. That's good. Filters working as intended. Whatever survives all that becomes candidate number one.
What's coming that could actually change the situation beyond just more maps?
CMB polarization with sensitivity to ultra-weak B modes. CMB spectral distortions, mu and Y types, to catch tiny energy injections in the early plasma. 3D 21-centimeter tomography of hydrogen over gigantic volumes, a direct view of structure growth. And the big trump card, space-based gravitational wave observatories to see broad stochastic backgrounds from early phase transitions. In parallel, deeper galaxy and quasar surveys with better systematics will tighten the constant variation story. The key is joint analysis. One faint hint means little. 3 independent faint hints, aligned in scale and physics, count as science.
For our listeners who want one honest line today, there are no traces of other universes, or traces are possible but not yet found.
Honest line: we know where and what to look for. Current data place serious bounds. No signal has yet cleared all checks. That's not disappointment. It's a normal phase of a big search program. We've learned to pose the right questions and to build experiments that answer not believe, don't believe, but effects of size X are excluded, size Y remains open. By cosmology standards, that's huge progress.
Then our arc really is complete, from infinity and inflation to domain walls and gravitational waves, without overpromising once. For the episode's final question, if we can separate data from fantasy this carefully, why does black hole as portal survive in pop culture? And can we state clean boundaries where math allows bridges but physics closes them?
Let's say it plainly, without smoke machines. General relativity lets you draw bridges, wormholes, and elegant space-time patterns. But once you add stability, quantum corrections, real plasma, and causality, those bridges collapse. Beautiful on paper doesn't mean traversable in nature.
And this is exactly where discipline beats temptation. Black holes aren't doors. They're laboratories. They test geometry, energy, and theory at a precision that sounded like sci-fi not long ago. If new physics is going to be born anywhere, it won't be in a cinematic portal. It'll be in a mismatch between a number on a detector and a formula in a paper.
We went from does the universe have an edge to does it have neighbors, and chose data over desire every time. Strangely, that gives more hope than any fairy tale. With an honest method, the road continues, even if there isn't a super Boeing hiding in a wormhole just around the bend.
Thanks for staying with us, for the sharp questions, and for keeping us honest. Keep them coming. Your questions become good experiments and careful theories.
If our way of unpacking hard topics resonates with you, no mysticism, but plenty of respect for imagination, support the show. Subscribe, rate, and tell us in the comments what grabbed you and which facts you want tested next time. Your shares are our booster to new listeners.
Next season, we'll shift from why it works this way to how to measure it harder. Shadows of supermassive black holes, stellar orbits in galactic centers, the gravitational wave background, and tomography of the early universe. Fewer metaphors, more tests.
This was Does Time Exist? Explained by an MIT physicist, a podcast that keeps the cosmos wondrous and true. I'm Emma Harper.
And I'm physicist Dr. Nathan Cole. Guard your curiosity. It's the only speed that doesn't depend on the metric.
See you next episode. Bye-bye.